Hello everyone, welcome to lecture 2 of chapter 6 where we will continue with subtopic 6.2 equilibrium constant. In this subtopic, at the end of the lesson, students should be able to define homogeneous and heterogeneous equilibria, write expression for equilibrium constant in terms of concentration Kc and the partial pressure Kp for both homogeneous and heterogeneous system. Next, define the degree of dissociation alpha and write the expression for reaction quotient Q. Let's start with the difference between homogeneous equilibrium and heterogeneous equilibrium. For homogeneous equilibrium, the products and reactant are in the same phase. For example, here we have N2O4, which is in the gas phase, decomposed to form 2NO2, which is also in the gas phase. Or we have 2SO2 gas react with oxygen gas to produce SO3, also in the gas phase. Meanwhile, for heterogeneous equilibrium, the product and reactant are in more than one phase, or product and reactant exist in different phase. So, for example, here we have calcium carbonate in the solid phase decomposed to form CaO solid plus CO2 gas. Or we have ammonium chloride NH4Cl in the solid phase decomposed to form ammonia gas plus HCl gas. Or we have hydrogen gas plus bromine liquid react to form 2HBr gas. Now we focus on the writing Kc expression. Okay, so the letter K represent equilibrium constant, while the subscript C in the Kc expression represent the concentrations of the reacting species. Now consider we have this general equation. AA gas plus BB gas produce CC gas plus DD gas. Okay, so the Kc expression will be the concentration of the product species rise to the power of its mole coefficient over concentration of reactant rise to the power of its mole coefficient. For example, here we have N2O4 gas decomposed to form 2NO2 gas. So the Kc expression will be the concentration of NO2 rise to the power of 2 since the mole coefficient is 2 over concentration of N2O4, which is the reactant species. Next, we have CH3COOH, which is in the aqueous phase, dissociates to form CH3COO-, which is in aqueous phase, plus H+, which is in aqueous phase. So the Kc expression will be the concentration of CH3COO- times concentration of H+ ion over the concentration of the reactant, which is CH3COOH. Note that, and please highlight this, the unit of concentration of each species must in the unit of molar or mole per liter. Next, writing Kp expression. So here the K represent the equilibrium constant. And the letter P, the subscript P in the Kp expression, it represent equilibrium partial pressure of the reacting gas species. And please take note that only the species which is in the gaseous phase will be involved in the Kp expression. For example, here we have, so the Kp expression for this general reaction will be partial pressure of reactant C to the power of small c times partial pressure of product D to the power of small d over partial pressure of reactant gas A to the power of small a times partial pressure of gas B rise to the power of its mole coefficient B. For example, here we have N2O4 gas decomposed to form 2NO2 gas. So the Kp expression will be P, the partial pressure of NO2 gas, rise to the power of 2 since the mole coefficient for NO2 is 2 over partial pressure of the N2SO4 gas. Here we have nitrogen gas plus 3 hydrogen gas produce 2 ammonia gas. And reminder once again, before we writing the KP expression, you should check that the reaction has already balanced. So the KP expression for this reaction above is the partial pressure of ammonia gas rise to the power of 2 since the mole coefficient is 2 over the partial pressure of nitrogen gas times the partial pressure of hydrogen gas rise to the power of 3 since the mole coefficient for the hydrogen gas is 3. And highlight this because this is also important. The unit of pressure for each of the gaseous species must be in the unit of atm. And please highlight this as well. The equilibrium constant expression, which is Kc and Kp, are also called equilibrium law. And please bear in mind as well that the Kc and Kp value is a dimensionless or no unit quantity. For example, here, given the Kc value for reaction between PCl3 gas and Cl2 gas to produce PCl5 gas is 1.67 no unit at 500 Kelvin. And given the Kp value for the reaction above is 4.07 times 10 to the power of -2 at 500 Kelvin. So both these value has no given unit. So in quoting a value for the Kp or Kc, you must specify the balance equation first. Okay, make sure the equation is balanced and including the phase of each reactant or product must be annotated well, and also given the temperature of the reaction. For example, let's do this example together. So the instruction is write expression for Kc and Kp if applicable for the following reversible reaction at equilibrium. So note, please balance the equation first. For A, you have HF aqueous dissociates into H plus ion plus F minus ion. So to write the Kc expression, so both species involved in the Kc expression, so the concentration of H plus times concentration of F minus over the concentration of reactant, which is HF. For B, 2NO gas plus oxygen gas produce 2NO2 gas. So the Kc expression will be concentration of NO2 gas to the power of 2 over concentration of NO to the power of 2 times concentration of oxygen gas to the power of 1. And since the species, the reactant and product species also in the gas phase, so this reaction also have a Kp expression. So the Kp value or the Kp expression is the partial pressure of NO2 gas to the power of 2 over partial pressure of NO2 gas to the power of 2 times partial pressure of oxygen gas. For C, the Kc value will be concentration of NO2 to the power of 4 times concentration of O2 to the power of 1 over concentration of N2O5 to the power of 2. And this reaction also has a Kp expression, which is the partial pressure of NO2 to the power of 4 here times partial pressure of O2 to the power of 1 over partial pressure of N2O5 to the power of 2. Now let's focus on writing Kc and Kp for heterogeneous equilibrium. So heterogeneous equilibrium is the reactant and product are in different phases. For example, here we have calcium carbonate, which is in solid, decomposed to form CaO solid plus CO2 gas. So when we're writing the Kc value, so the Kc represent concentration of product CaO times concentration of CO2 over concentration of CaCO3. However, class, we could ignore the concentration of CaO in this reaction since the CaO reactant appear in the solid phase and also the CaO also appear in the solid phase. So the concentration of pure solid, pure liquids, and solvent do not appear when we writing the equilibrium constant expression. Okay, because it is impossible for us to measure the concentration of pure solid, pure liquid, and pure solvent. Okay, so the Kc expression only involve substance in the aqueous phase and also in the gas phase. So the Kc expression for this reaction is only equals to the concentration of CO2 gas. And the Kp expression only involve CO2 gas because it is only substance that exists in the gas phase. So Kp is equals to the partial pressure of CO2 gas. So let's try this activity together. Activity 2. So write expression for Kc and Kp if applicable for the following reversible reaction at equilibrium. So the value of concentration and the partial pressure of each species is the value of the species at equilibrium. So one we have HF aqueous plus H2O liquid produce H2O plus ion aqueous plus F minus aqueous. So for Kc value, so concentration H3O plus times concentration of F minus, both in the aqueous phase, over concentration of HF only, since H2O appear in the pure liquid. So pure liquid does not involve in Kc expression. Okay, for number 2, NH4 solid decomposed to form ammonia gas plus HCl gas. So the Kc expression is only concentration of ammonia, since it is in the gaseous phase, times concentration of HCl, the gaseous phase. And the reactant NH4Cl is not included in the Kc expression since it is in the solid phase. And the Kp expression for this reaction is equal to the partial pressure of ammonia gas times partial pressure of HCl gas only. And number 3 Roman, H2O liquid plus SO2 gas produce H2SO4 aqueous. So the Kc expression is the concentration of H2SO4 over concentration of SO2 because Kc only involve substance in aqueous and gas phase only. But for Kp, the product side, there is no compound that exists in the gaseous phase. So we substitute with number 1. So 1 over concentration of the reactant species. So only SO3 gas involved in the Kp expression. So 1 over partial pressure of SO3 gas.